Welcome to The Explainer. Today, we're going to pull back the curtain on the tech that's behind, well, almost everything these days. From self-driving cars to those mind-blowing AI art generators. We're talking about neural networks.
So what if a computer could learn like a human brain? I mean, really think about that for a second. We're not talking about a machine that just follows a set of rules. We're talking about something that learns from experience, that can actually adapt, see patterns, and just get better over time. Kind of like a digital apprentice. That's the huge idea we're going to unpack. Okay, so here's how we're going to break it all down. First, this whole idea of the brain in a box. Then we'll look at the anatomy, what they're made of. After that, we'll dive into how they learn, check out some specialized types, and finally, look at the big picture, what this all means for all of us. All right, first up, the brain in a box. So what are we really talking about here? Well, at its core, a neural network is a machine learning model, but it's one that's inspired by, you guessed it, the most incredible computer on the planet, our own brain. So what that really means is we've basically built a system of interconnected software neurons. And, just like the neurons in our own heads, their whole job is to find and make sense of complex patterns in whatever data you throw at them. You can literally think of it as an artificial brain built from the ground up specifically to learn. Okay, so if we were to pop the hood on one of these digital brains, what would we see? Well, like any complex system, it all starts with a few fundamental building blocks. Let's break down the three key parts of its anatomy. The absolute heart of the whole thing is the neuron, or you'll also hear it called a node. This is the basic building block, right? Think of it as a single brain cell. It's just a tiny little processing unit that takes in some information, does a super quick calculation, and then passes its result on to the next guy. Okay, now this is where the real magic happens, the weights. These are basically little numbers that determine how strong the connection is between any two neurons. If a weight is high, that connection is super strong, and that neuron signal has a lot of influence. And here's the kicker. Adjusting these weights, that is how the network learns. It's everything. And the last piece of the puzzle is called bias. The best way to think about it is like a little thumb on the scale. It's just an extra parameter that gives the neuron a bit more flexibility. It helps it shift its output up or down, making it easier to fit the data just right. So, this image really puts it all together for a single neuron. You see the inputs coming in from the left? Each one gets multiplied by its own special weight. That's how we decide its importance. Then, all those weighted inputs get added up. The bias gives it that final little nudge, and the whole thing is passed through something called an activation function. And that's basically just a little gatekeeper that decides, okay, is this signal important enough to pass on or not? It's a simple process, but when you have millions of these neurons all doing this at once, well, that's where you get some serious power. Okay, we've got the parts, but how does this thing actually get smarter? How does it learn? Well, it's actually a lot like how we learn anything new, through a whole lot of trial and error. The whole process of training is really just this simple loop, repeated over and over. The network makes a guess, it checks to see how wrong it was, and then, and this is the most important part, it uses that mistake to go back and tweak all its internal connections, just a tiny bit, to make a better guess next time. And this whole learning process is really a two-step dance. First, you have what's called forward propagation. That's the easy part. The data just flows forward through the network and it spits out a guess. But then comes the really clever part, back propagation. This is where the network calculates its error and then works its way backward through all the layers, telling each and every connection exactly how to adjust its weight to do better. That right there is the learning. But wait a second, how does the network even know how wrong it was? Well, that's the job of the loss function. Just think of it like a score in a video game. After every single guess, the loss function gives the network a score. A really high score, or high loss, means you were way off. A low score is great. So the entire goal of training is just to keep playing this game over and over, tweaking those weights and biases each time, trying to get that loss score as close to zero as possible. Okay, so just like our own brains have different areas for vision, language, and so on, these digital brains aren't one size fits all. Different problems call for different kinds of networks, each one specialized for a very specific job. And this table gives a fantastic snapshot of the big three. You've got your CNNs. Think of these as the visual brains. They are masters at looking at images and picking out objects, like for facial recognition. Then you have RNNs, these sequential brains. These guys have a kind of memory, which makes them great for understanding things in order, like language. And then you have my favorite, the GANs. These are the creative brains, and they are just wild. GANs are seriously cool. The way they work is by having two neural networks basically fight each other. You have one network, the generator, whose whole job is to be an art forger. It tries to create brand new, totally fake data. Then you have the second network, the discriminator, which is like an art detective trying to tell if the data is real or fake. This constant battle forces both of them to get incredibly good at their jobs. And you can see that whole game playing out right here. The generator starts with just random static and tries to create something that looks real, in this case, a handwritten number. Then its creation gets mixed in with real examples and shown to the discriminator. And the discriminator's only job is to say real or fake. As you can imagine, this competition is what forces the generator to produce fakes that are almost indistinguishable from the real thing. Okay, so this is way more than just a cool theory, right? Let's get into our final section and talk about the impact. Let's look at how these digital brains are already out there changing our world and what might be coming next.
Really, the best way to think about neural networks is as the engine that's driving the entire AI revolution. Seriously. Anytime you hear about a huge breakthrough in deep learning or some new AI that can do something that seems almost magical, odds are this is the technology that's making it all happen.
And this is why it really matters, to you and me. This stuff is what's automating complex jobs to make things more efficient. It's the reason the recommendations you get on Netflix or Amazon feel so spot on. And of course, it's the absolute core technology that's making things like self-driving cars a reality. It's not science fiction anymore. It's here, and it is changing everything. So that really leaves us with one last big question to think about. When you have a technology this powerful, one that can literally learn and adapt on its own, the possibilities are just mind-boggling. I mean, we're talking about medicine, climate change, art, you name it. So the real question isn't just what can these digital brains solve, but what problem do you hope they tackle next?